Hello everyone. Welcome to ILTA Physics Online. Today we're going to be studying the moment of inertia. Think back to our last lesson where we discussed how torque is the rotational equivalent of force. Similarly, the moment of inertia is the rotational equivalent of mass. To put it more simply, it's a measure of how difficult it is to change an object's rotational motion. As an example, think about a figure skater spinning. Do you remember how a skater, spinning in place with their arms extended, starts to spin faster and faster as they pull their arms in toward their chest? The principle behind that change in rotation is exactly what we're studying today, the moment of inertia. For today's lesson, we'll start with a brief overview of rotational dynamics in general, and then we'll define the concept of the moment of inertia. Then we'll derive how to calculate the moment of inertia for a given object. Finally, we'll analyze rotational motion from a dynamical perspective by applying Newton's second law, which we usually use for linear motion to rotation. So let's quickly review what we covered last time before we dive into today's class. Last time, we studied the torque caused by gravity acting on an object. If there is a proper axis of rotation, gravity on Earth can act as a torque that causes an object to rotate. As you can see in the diagram below, a pencil leaning at an angle will rotate and fall to the left, using the edge touching the desk as its axis of rotation. To analyze this kind of rotational motion caused by gravity, we define the concept of the center of mass. Previously, we learned how to calculate the torque produced by a force acting on a specific single point of an object relative to a specific axis. We found that torque is the product of the perpendicular component of the force applied and the distance to the axis of rotation. However, since gravity acts on every single part of an object, we can't really analyze rotational motion by looking at the torque on just one tiny section. This is why we introduced the concept of the center of mass. We assume all of the object's weight is concentrated at one single point to analyze the torque created by gravity. It's the similar idea as using a particle model in kinematics, where we represent an object as a single point regardless of its actual shape or size. This center of mass idea is really useful for determining if an object is balanced based on its position relative to the axis of rotation. In other words, if the center of mass and the axis of rotation are perfectly lined up vertically, no torque is generated. This means the object won't rotate, it won't fall over, and stays balanced. We can derive the method for calculating the center of mass from the physical fact that the torque due to gravity is zero when the axis of rotation coincides with the center of mass. By setting up a relationship where the vector sum of the torques acting at each position is zero at the center of mass, as shown in the bottom right figure, we were able to derive the coordinates for the center of mass. We have seen that this way of modeling objects can be extended to calculating the center of mass for complex objects encountered in real-world problems by breaking them down into multiple pieces. Now, with those concepts in mind, let's go a bit deeper into rotational motion. So far, we've been analyzing rotational motion from two different sides, kinematics and kinetics. Kinematic analysis looks at the relationship between angular position, angular velocity, and angular acceleration. On the other hand, kinetic analysis looks at rotation from the perspective of torque, which is what actually causes the rotation. Today, we're going to connect these two, kinematics and dynamics, and analyze rotation from a rotational dynamics perspective. Through this, I'll introduce a very interesting physics concept called the moment of inertia. Let's think about the motion of a merry-go-round like the one in the picture on the right. I'll explain this by comparing it to linear motion, which we already know well. In linear motion, Newton's second law tells us that the force applied to an object creates acceleration. The quantitative calculation of this intuitive relationship between force and acceleration is F equals ma. To put it another way, the force applied is proportional to the acceleration, And that constant of proportionality is the mass of the object. From the perspective of motion, this means it takes a larger force to accelerate an object with more mass. In other words, mass is a physical factor that resists or makes it difficult to change an object's motion. Up until now, we might have just thought of mass as how heavy something is. But from a dynamics perspective, it's a factor that resists motion. You could call this a shift in perspective. Now let's apply this same idea to rotational motion. In rotation, torque creates angular acceleration. Just like F equals ma, we can intuitively expect that torque and angular acceleration will be proportional to each other. So, what is the physical factor that connects torque and angular acceleration quantitatively? What is the rotational version of mass? That is our topic for today. The moment of inertia. Simply put, the moment of inertia is the rotational equivalent of mass. As the name suggests, inertia defines this quantity as a measure of how much an object resists rotation from a dynamics perspective. But isn't the word moment a bit weird? In moment of inertia, the word moment has nothing to do with time. It actually comes from a Latin root meaning motion. In conclusion, from a dynamic standpoint, we can summarize it like this. Just as mass measures an object's resistance to linear acceleration, the moment of inertia measures its resistance to angular acceleration. So, how do we derive this moment of inertia? Let's go back to the merry-go-round. From a kinematics perspective, the tangential acceleration at the outer edge can be calculated as the product of the angular acceleration and the distance from the axis of rotation. Also, from a kinetics perspective, the torque at that position is the product of the perpendicular force applied and that same distance from the axis. Using these two physical relationships, we'll quantitatively derive the moment of inertia on the next page. Now let's take a detailed look at the center of mass. Imagine a long rod where one end is the axis of rotation, and the other end is moving in a circle around that axis, as shown in the figure on the right. In this case, the entire rod is rotating, and every part of the rod is performing circular motion. Let's focus on the very tip of the rod. That tip is moving in a circular path. We are going to analyze this motion by dividing it into two perspectives: the macroscopic view of circular motion and the microscopic view of linear motion in the tangential direction. First, let's take a look at the circular motion from a macroscopic perspective. As I mentioned before, to analyze an object in circular motion kinematically, we need to consider three directions of motion. First is the centripetal direction pointing toward the center of the circle. Second is the direction of angular velocity following the arc of the circle. And finally, there's the tangential direction, which points along a straight line perpendicular to the radius at any given moment. Let's look at the circular motion of the tip of the rod from a macro perspective first. For an object to move in a circle, its direction of motion must change every single second. Therefore, a centripetal force must be acting toward the center. In this case, that force appears as tension in the centripetal direction, and this force creates centripetal acceleration. This centripetal acceleration is what constantly changes the velocity's direction, keeping the object on its circular path. This is a review of what we covered when we first discussed circular motion. It's the dynamical explanation for why an object stays in a circular orbit. Today, however, I want to look at it from a micro perspective, focusing on the tiny movements over a very short period of time. Specifically, we'll look at the angular and tangential directions. From a micro perspective, over a very short time interval, the rotation can be thought of as linear motion in the tangential direction. The force moving the object in the tangential direction creates tangential acceleration. The relationship between this tangential force and tangential acceleration follows Newton's second law. F equals ma. Now, in circular motion, this tangential acceleration can be expressed as the product of the angular acceleration and the distance from the center. Stay with me here. We are looking at the rod's rotation simultaneously as a microscale linear motion called tangential motion, and a macroscale circular motion, angular. Next, let's look at the tip of the rod from the perspective of torque. This same tangential force creates torque, which we can calculate by multiplying the tangential force by the distance to the axis. Please note that the tangential force and the radial line connecting it to the axis are perpendicular to each other. If we combine these two equations and solve for angular acceleration, we get a specific relationship. We now have an equation that looks just like Newton's second law, but expressed purely in terms of rotational variables, torque and angular acceleration. If we rearrange this back into the familiar F equals ma, it looks like this: tau equals mr squared times alpha. Here, we define the term that quantitatively describes the proportional relationship between torque and angular acceleration as a moment of inertia. In essence, the moment of inertia is the rotational variable equivalent to mass in linear motion. That covers how to derive the moment of inertia for one single point of a rotating object. Please make sure to memorize this final formula. Okay, we've derived the relationship between torque and angular acceleration for one part of a rotating object. Now let's find the moment of inertia for an entire rotating object. As I've mentioned, since rotation and circular motion are closely related, every tiny piece of a rotating object is essentially moving in a circle around the axis. We just derived the formula for torque on one of those tiny pieces. To calculate the net torque for the whole object, we'll use the rigid body model. We'll imagine the object is divided into many tiny pieces, calculate the torque for each piece individually, and then add them all up. We can calculate the torque for each piece using the formula we just derived like this. Crucially, every single tiny piece of a rotating rigid body shares the exact same angular acceleration. We'll use this fact to define the moment of inertia while calculating the net torque. Imagine the object in the right-hand figure is rotating around the axis on the left. Let's calculate the torque for three representative parts, position 1, 2, and 3. First, the torque at position 1 is the product of its mass, the square of its distance from the axis, and the angular acceleration. Following the same method, the torque at position 2 is its mass times the square of its distance times the angular acceleration. It's the same for position 3. Since these are all parts of the same object, they have the same angular acceleration called alpha. When we factor that out, the equation looks like this. In other words, the net torque on the entire rotating object is the product of the angular acceleration and the sum of the mass times distance squared for every point in the object. We call this sum the total of every piece's mass times its distance from the axis squared, the moment of inertia. As you can see from the formula, the further a mass is from the axis of rotation, the larger the moment of inertia becomes. Now let's wrap up today's lecture by summarizing the rotational equivalent of Newton's second law. Just like F equals ma in linear motion, the torque in rotational motion is the product of the moment of inertia and the angular acceleration. Tau equals I alpha. The moment of inertia, I, is calculated as sum of mr squared. As the name implies, an object with a large moment of inertia requires more torque to change its rotation. Physically, you can think of the moment of inertia as a ruler for how hard it is to get an object to rotate. If the net torque on an object is 0, its angular acceleration will be 0. This happens if the object isn't rotating at all, or it's rotating at a constant angular velocity. Below is a table comparing force, mass, and acceleration in linear motion. to their counterparts: torque, moment of inertia, and angular acceleration in rotational motion. Please compare these and make sure you understand how they correspond. Also, pay close attention to the units for each quantity. Finally, here is a table of the moments of inertia for various shapes that we will deal with frequently. Fortunately, we won't be deriving the formulas for these shapes ourselves. You just need to memorize the results. One thing to be careful about: even for the same shape, the moment of inertia changes depending on where the axis of rotation is located. Also, keep in mind that whether a shape is solid or hollow is a big factor that changes the moment of inertia. That's it for today's lecture. Great job, everyone. See you next time.